The purpose of this video is to show an example of how to use an ice chart to solve a problem that asks you to determine the limiting reactant in a chemical reaction. So let's review the parts of the ice chart. You have a picture where you can draw the particle models that represent the problem, and you have another one down here at the bottom. This is for the initial before the reaction. This is the end after the reaction. I stands for initial, E stands for end, C stands for change. At the same time that we're drawing these particle models, we're also going to be using symbols to represent what we have initially, what happens during the change, and what we will have left over at the end of the reaction. So let's get started by looking at the question. It says we've been given 8 moles of aluminum and 6 moles of sulfur and asked which is limiting and which is in excess. Let's start by drawing the picture. 8 moles of aluminum, or you could think of it as 8 particles of aluminum. Those are my 8 particles, or 8 moles. Remember, particles and moles can be thought of the same amounts because all particles are equal in ratio to the number of moles of that same number. So if I said I had 2 aluminum atoms, or I could think of this coefficient as 2 moles of aluminum, we'll combine with 3 atoms of sulfur, or 3 moles of sulfur. So however you want to say it, particles, atoms, moles, this ratio 2 to 3 to 1 is going to hold up, whether it's particles or moles. And we prefer moles because those can be easily measured in the lab with grams, and it's very, very hard to count particles. So we'll stick with moles. 8 moles represented by 8 triangles. Now I need 6 moles of sulfur. 1, 2, 3, 4, 5, 6. And initially I have 0 of the product left, or 0 of the product to begin with. So I then have my numbers here, and I'm going to actually write 8 moles, 6 moles, and 0 moles to show that's what those numbers mean. Now during the change, this is where I have to try a couple of different things, because we have 2 reactants, aluminum and sulfur. Both of them could be limiting. What does it mean to be a limiting reactant? Well, it means that's the reactant that is used up first. It's completely used up in the reaction. So let's pretend that these 8 moles are going to be completely used up. We can use an equation to describe that. 8 minus 2x equals 0 aluminum in the end. Why did I say 2x? Because we have a ratio here, 2 to 3 to 1. And I have to keep that ratio going. 6 minus 3x could equal 0 sulfur in the end. And I have to decide which of these 2 is actually correct. Whichever one of these 2 is the limiting reactant is going to help me determine how many moles of product I have at the end. So you see the 2 to 3 to 1 ratio here is evident in the 2 to 3 to 1 ratio here. So I'm keeping my mole ratio the same, but I don't know the value of x yet. X could be 4, because 8 minus 4 equals, 8 minus 2x, 2 times 4, equals 0. So that's one possibility. Or x could be equal to 2. 6 minus 3 times 2 is 0. 6 minus 6 is 0. So which one is correct? We always choose the smaller of the 2. This is correct. This one is not. So I know that this isn't going to be 0 anymore because it's no longer 8 minus 2 times 4. I know that the value for x has to be 2. So how do I fill that in without a whole bunch of erasing? I like to do it this way. Instead of saying 2x, instead of erasing x and putting a 2, I'm just going to let x represent the multiplication sign now. 8 minus 2 times 2. 6 minus 3 times 2. 0 plus 1 times 2. So you can see what I did is I chose the smaller value of x because I know that sulfur is going to run out first because its value for x is lower. And then I substituted x with that number, 2. And now I'm going to finish my subtraction. 8 minus 2 times 2 is 4. 8 minus 4 is 4. That's 4 moles of aluminum at the end of this reaction. Another equation to finish up is 6 minus 3 times 2. That's 0 moles of sulfur. And we had already predicted, since 2 is smaller than 4, that we'd run out of this, and you can see we have. And then finally, how much product do we have? 0 plus 1 times 2 is 2 moles Al2S3. Okay, now another way to get to these same conclusions would be to draw some pictures. So I want to draw those pictures here, and you'll see that this will confirm the numbers that we just arrived at. So if I'm going to build aluminum sulfide from triangles and circles, I need 2 triangles for every 3 circles. So there's 1, 2, 3 circles connected to 2 triangles. So I've consumed 1, 2 triangles and 1, 2, 3 of my circles. I still have enough to make another set. In fact, I'm going to make a second set. 1, 2, 3 circles. 1, 2, 3 more circles, and 2 more triangles. 1, 2 more triangles. So what this is showing me is that at this point I have used up all of my sulfur. So there is 0 sulfur to move down here. Instead, they've all moved over to the product side at the end of this reaction. My little dots in here show me that I've used up these guys, and they're now present in the reactant side. And I still have 1, 2, 3, 4 left, and I can draw them in here. Now this is a great way to show the law of conservation of mass. The atoms from the reactant side are still present in the product side, but the ones that were not used remain as excess. So what have we figured out? We have 4 moles of aluminum in excess. We have no moles of excess sulfur, or we can say sulfur is our limiting reactant. And we have 2 moles of aluminum sulfide, represented by these particle models here on the right side. So to get back to answering our question, we wanted to circle the limiting reactant, and our limiting reactant was sulfur. We know the excess is aluminum down at the bottom, 4 moles and 2 moles of product. The next step is to say, well, how many grams is 2 moles of aluminum sulfide? How many grams of product have we made? How many grams of aluminum remain behind? How many grams of sulfur have we used up? These are all things that we can do with these types of problems before and after we use the ice chart. In the next problem, we'll do hydrogen and oxygen and determine which one of those is limiting in the production of water.